All right. This is AP Chemistry Notes. Pages, where are we now? 80 to 82 on buffers. It's the last lesson for acids and bases. And students often say that they find this one pretty complicated. But if we can relate it to a titration, it shouldn't be too bad. So I'll do that throughout this lesson, and then I'll actually go back to our last lesson where we really looked at a titration, and I'll show you where we had a buffer and where we didn't have a buffer. So let's jump into the main event here. The typical definition is that it resists a change in pH when reasonably small amounts of acid or base are added. So you have a solution at a particular pH, and a little bit of hydrochloric acid is added, or a little bit of sodium hydroxide is added, and the solution essentially absorbs the added thing and keeps the pH either exactly the same or very close. Now, notice it says small amounts. There is a point at which you ruin the buffer, and at that point, it's not keeping the pH constant. We'll take a look at that as well. So to make a buffer, what you need is you need a reasonable combination of a weak acid and its conjugate base. So for example, you could take the weak acid HF and its conjugate base F minus. Or you could take the weak acid phosphoric and its conjugate base dihydrogen phosphate. And there are many combos like that. Now, the pH that these solutions would have would vary, and we'll get into how to figure that out. But both of these systems here would be considered buffers. Now, you might be thinking, well, if I have HF by itself, doesn't HF automatically make H plus and F minus? So if I have HF, don't I also have F minus? Well, you do, but you don't have a significant amount of F minus. You have this much HF and you have that much F minus, and that's not enough to consider it a buffer. In order to be a buffer, you have to have a significant amount of both HF and F minus. And that's why the HF alone is not a buffer. And likewise, F minus alone is not a buffer. So there's a couple different ways you can make one of these buffers. The first way here is simply just add the two things together. So take a weak acid, I just called it HA to be generic, and its conjugate base, A minus. Now, I mentioned in a prior lesson, you can't have A minus by itself in a jar, but you can have sodium A minus or potassium A minus. So the sodium here is not really doing anything other than that's the way the chemicals exist. So you can just take a handful of HA and a handful of NaA and stick them together. The other way you can do it is you can start with one of these. So start with either just HA or just A minus and react some of it to its conjugate. So in the case of HA, we could add some hydroxide and we will get some A minus. And it's this combo of HA and A minus that is the buffer. If you wanted to start with A minus here, you could add some strong acid and you could make a significant amount of HA, and you'd be making the same buffer system either way. And you can do it any of these three ways. So 1, 2, and 3, you could make the exact same buffer any of those three ways. As long as you end up with a substantial amount of both weak acid and its conjugate weak base, then you have a buffer. Now I mentioned over here, you'll see I have this titration graph. When you do a titration, you're essentially starting with just weak acid, usually. And the idea is to completely react the weak acid until it's gone and you've made A minus. So that would be the endpoint here. These 2 points are not buffers. So, not a buffer. That's just HA with the tiniest bit of A minus. Likewise, here, not a buffer. That's the opposite situation. Where we have a buffer is right in here. Right in the middle is a great example of a buffer because half of our HA has been turned into A minus and half of our HA remains. So that is a buffer right there in the middle. And you could also argue that to the sides here and here, that would also be a buffer with slightly different pH because you have a combo of both weak acid and conjugate weak base. So let's say you want to make one of these things and you want it to be at a certain pH. Well, there's a way to actually make that happen. So how to choose chemicals to make a buffer. Where you want to start is, actually, let me go back to that graph. You want to start assuming that you're right in the middle of the titration. So start right here in that midway point where you have exactly equal HA and A minus, and just see where that takes you, and then you can modify it as needed. So at that point, if we have exactly equal HA and A minus in the Ka expression, those two things cancel. Now I have Ka equals H plus. If you take the negative log of both sides, you get pH equals pKa. In other words, the pH of the solution, which happens to be a buffer, will be equal to the pKa of the weak acid. So let's take a look at an example, and that should help. Let's say, for some reason, we want to buffer with a pH of 5. And let me stop and talk about why you might want to buffer, because that'll help. Often, especially in biological systems, the organisms need to be in a particular small range of pH, otherwise they don't survive. And so when doing biological experiments, if you don't run your experiment in a buffered solution, everything just dies and it's pointless. So that's one reason to have a buffer. If you take AP Bio or some biochemistry classes in college and so on, you will likely see this. And I remember one that was really popular was called a phosphate buffered solution. And it helped keep the tissues and organisms useful. Another example would be human blood. Our blood, I don't remember the exact, I got to use red for this, but blood has to have a very certain pH, and the range is pretty tight. If it changes very much, like let's say it goes up by a pH 1 or down by a pH of 1, many of the reactions that we need to happen in our blood don't work correctly anymore or at all, or maybe they go too fast, and you'll be very sick if you're even surviving anymore. So it's a really big deal that our blood is buffered. Obviously, we don't think about it. Fortunately, nature does that for us most of the time. But let's say we want a pH, back to the problem, of 5, which is going to be a little bit acidic, not too much. And let's say we have 3 acids at our disposal. Ammonium, so it would be like ammonium nitrate or dihydrogen phosphate. So that would be like sodium dihydrogen phosphate or acetic acid, which of course is vinegar. Let me make sure that is acetic acid. See, C2H3O2 would be the same as CH3COO. And then they've put a hydrogen on it, so that should work out. So 2 carbons, yeah, that's acetic acid there. I prefer this version here because it actually looks more like what the Lewis structure would be. I think we've talked about that in the past. Anyway, these 3 acids, of which I left off some of the spectator ions on acid 1 and 2, don't worry about it, have the relative Kas. And so the question is, which one would be a good one to just at least consider for a buffer with a pH of 5? Now, by the way, all of these acids by themselves are not a buffer. This is just a good starting point. Well, if you were to take the negative log, let me get a color here, of each of these, you get roughly the exponent, 10, 8, and 5. I'm ignoring the numbers in the beginning. So clearly, in this case, the best one is number 3. So let's take that acetic acid and let's make a buffer and see what the pH turns out to be. So moving along, let's say we take the acetic acid from earlier. So CH3COOH, which is acetic acid, or the way I wrote it earlier, I put the hydrogen in the front right here. Either way is fine, but this is the more normal version, like that. Rather than writing that over and over again, I'm just going to call it HA and NaA. Again, the reason I have to put that sodium is because I can find a bottle of sodium acetate and I can find a bottle of acetic acid, but what I can't find is a bottle of just acetate ion. It doesn't exist by itself. So that's why the sodium's there. And other than having to factor in molar mass when you're doing grams, you can just ignore it. So let's do it with a perfect equal ratio where we have 0.2 moles of acid and 0.2 moles of conjugate base. And this is the pH that we had from the prior problem, 1.8 times 10 to the negative 5, which came from right here. Well, we're going to focus on the acid for a moment. HA does what weak acids do. Here's the Ka expression. Take the moles, divide by the volume, which is pretty convenient this time, and we get 0.2 molarity weak acid and 0.2 molarity conjugate weak base. Plug those into the Ka expression here and here. And they cancel, which says H plus is equal to the Ka, which was in the proof on the earlier page, and pH equals the pKa, which you might have thought, hey, why are you bothering doing all this work? Why are you bothering calculating these molarities and plugging these in there? Didn't we know that pH equaled pKa? Yes, we did, but I wanted to show it anyway. It's nice to see it in action, but you could have made that jump of logic. And notice our pH is 4.74. So that's pretty good. We chose well. It's close to a pH of 5, not exactly. And depending on what we're doing, that might be good enough. We might be able to just go with this and just make this, as I've stated, and move ahead. But let's say we are going to be really picky and we want the buffer. I'm down here now. We are insisting we want it exactly at 5. Well, the problem with the one that we tried to make with equal amounts is the pH was a little too acidic. So what that means is we either need to lower the HA a little bit or raise the A minus so that they're not equal anymore. And that will raise the pH a little bit till we get to 5. I just made up this particular situation here. Same system. And let's say we already know that we have 1 liter of 0.1 molar weak acid HA from earlier. And so I just made that up so that we had something to start with. So let's just start there. So 1 liter, 0.1 molar HA. That means the HA is 0.1 molar. This is the Ka expression right here. So that's what I'm looking at. We know that the molarity of the HA is 0.1. We know the Ka. And we know that we want a pH of 5. That was what we're being insistent on. So the H plus is here. So you just plug that in, solve for it, and plug it in. And let's see, based on what the problem has given us, what's the concentration of A minus? Well, it turns out that it's 0.18 molarity. And notice it actually is a little higher than the HA. So the A minus needs to be 0.18, whereas the HA was 0.10. This is in 1 liter, so 0.18 moles of A minus, which means since we can't find a bottle of A minus, but we can find a bottle of sodium A minus, or let's go back to the real situation here. This is acetate. Again, I can't find a bottle of acetate, but I can find a bottle of sodium acetate. So we get 0.18 moles of sodium acetate. And if we use molar mass, we could turn that into grams of sodium acetate. We could weigh it out, and then we could add it to this solution. So this has shown 2 ways to make a buffer. This first way here, this one, we were adding weak acid and weak base together. And in the second one, we started with a weak acid. No, actually, let me take that back. We did it the same way. We actually made it the same way, but we just changed our amount. I was thinking we would do the other thing, but I didn't put that in here. All right, now let's take a look at how the buffer operates. In other words, let's take a buffer that exists and put stuff in it and see, does it indeed keep the pH relatively constant? You'll see my note here. We don't really have to get too detailed in here for the AP exam, but we'll cover the basics. All right, strong acid addition. In other words, you have a buffer and you are going to put some strong acid in it. You might say, well, why would you do that? There's just situations where as you do experiments, acids might get produced, or maybe you have to add an acid to cause a certain reaction to occur, and you need your buffer to keep things from going too out of whack. So as we expect, it either doesn't affect the pH at all, if you only add a little bit, or it might not affect it very much. And this is assuming the buffer survives. There's a point at which you can ruin the buffer, and I will show again where that happens. So if you add a strong acid to a buffer, you have to think about, well, which of the 2 things in the buffer is going to react with it? Well, it's the base. The conjugate base is going to react with the strong acid being added, which of course is just H+. So let's take a look. Let's use this example now. We'll switch to a new one. We've got the weak acid, lactic acid, which of course you heard of, it's what built up in muscles, and its conjugate base, lactate, which would be a complex polyatomic ion. I better phrase that correctly. It wouldn't be a complex ion, it would be a complicated ion. Don't mix that up with those complex ions that we've talked about recently. So we make a buffer and we take 1 molar lactic acid and 1 molar sodium lactate. Again, it's the lactate that we care about. And we make a liter. So the numbers are very nice right here, all ones. It turns out it has a pH of 3.85. If you take the negative log of the Ka, you'll get 3.85. We did that already. Well, not this exact one, but that process. Let's say we add an entire liter, which is a lot, of 0.1 molar hydrochloric acid. Now, it's not concentrated, but 0.1 molar hydrochloric acid, that's pretty acidic. By itself, it has a pH of 1. What's the new pH? It should say, what is the new pH of the final solution? Which could be a buffer still, or maybe it got ruined. Well, you need to think what is going to react. The buffer has two things in it. The buffer has HLAC, which is just short for lactic acid. We don't want to take the time to write out its chemical formula. And it's also got lactate. Well, the strong acid that's being added is going to react with the weak base. Here, that will be consumed, and it will, by accident, make much more of the lactic acid. So we're consuming the weak base, and we're producing the weak acid that's already in the buffer. And if we take a look at our numbers here, because it was 1 molarity of both lactic acid and lactate in 1 liter, I had 1 mole of each to start with. You see, I labeled this the original buffer. We added 1 liter of 0.1 molar hydrochloric acid, so that's 0.1 moles. And this is from the HCl. So the lactate will be consumed, hence the negative. The lactic acid will be produced, hence the positive. And you can see that my lactate went down from 1 mole to 0.9 moles. My lactic acid went from 1 mole to 1.1 moles. Notice we have a new volume because we added a liter to a liter. Our new volume is 2 liters. Divide by that, that gives my new molarity of both things in the buffer. The strong acid is gone. The strong acid H plus has been converted into this stuff. And you plug both these values into the Ka expression. So here's the Ka that was given. Here is the, let me switch to a new color, the lactate or weak base. Here's the lactic acid or weak acid. Solve for H plus, and you get this. And then you get a buffer with a pH of 3.77. And notice what's happened to the pH here. It started at 3.85 and it went down to 3.77 because we consumed some of the weak base and we made some of the weak acid. So it's no surprise that the pH went down, but it didn't go down very much. So you can see the buffer did what it's supposed to do. It buffered. And if we wanted to think, do we still have a buffer? Well, yeah, because we still have a significant amount of both species. So that's still a buffer. It's a buffer with a slightly different pH, but it is still a buffer. So looking at a titration graph, like I have here, we essentially were starting with this X here. That's right in the middle of what would have been a titration. Because of course, if we look at the volume of base, we started here. The end point is approximately here. And so that is the halfway point. It's not very accurate, but close enough. And so we started with that X that I have on the right that's circled in green. And by adding the strong acid, we moved a little bit to the left to this X, slightly to the left, slightly lower pH. It's almost like we were at the midway of a titration and we decided to go backwards for a little bit. I made a note up here that I intentionally ignored because I didn't think we were ready for it, but right here, this one. There's a lot of arrows and a lot of colors right now. An interesting note, the total moles of buffer species, meaning acid and conjugate base, is always the same. So if you look at this problem here, we had a total of 2 moles. I need a better color. Let me go highlighter. 2 moles of total buffer species. And afterwards, we still had 2 moles of buffer species. It was because when you add something to a buffer, you're going to consume one of the species, but that's going to make the other species. So it's interesting that that mole stays constant. Now notice molarity did not stay constant. Total molarity did not stay constant because it's getting diluted in this case because we were adding a volume to a volume. All right, let's take a look at a strong base. Same idea, except now the adding of the strong base is going to consume the weak acid in the buffer. So in this one here, let's say we have a buffer of hydrofluoric acid. I don't want to restart my computer right now. That would be inconvenient. And sodium fluoride. Again, fluoride is what we care about. And it says a little bit of solid sodium hydroxide is dumped in it. So like a little pellet or something. Which part of the buffer is being consumed, which is being produced. So this is just testing to see if you understand how a buffer works. Well, this is what's being added, sodium hydroxide. That's going to react with the weak acid in the buffer that gets consumed, and we make its conjugate weak base, which was already present, but will go up. Let's see, I got some notes here. Number 1. Oh yes, increasing the concentration of buffer components. That means the weak acid and the weak base. In other words, putting more of both. Keeps the pH the same, but increases the capacity. So we should talk about capacity. The capacity of a buffer is how much strong acid can be added before the buffer is ruined, or how much strong base is added before the buffer is ruined. And an example of that would be if I go up here, if we look at this buffer system, this 1 mole of each of those species is roughly the capacity. If we added more than 1 mole of hydrochloric acid in this example, it would have consumed all of the weak base and you wouldn't have a buffer anymore. So the capacity refers to that, as in how much strong acid or base can be added before the buffer is ruined. Note number 2, when a buffer has more conjugate acid than base, it has a greater buffer capacity for the addition of a base than an acid. It's because if you've got more conjugate acid, it can consume more strong base being added, and the opposite if you have more conjugate base than acid. Now I have this graph here, and normally we would have done the phosphoric acid lab, but we have not at this point. And it's just mentioning what's going on with during that titration. There are times where you don't have a buffer and there are times where you do have a buffer. I'm going to save this for class. and I'll set us up. We can discuss this in detail. I'll give you a little more background as to why the graph looks like that. We can talk about why certain areas are buffers and certain areas aren't. But before I finish, I do want to go back to our last lesson and show you where we had a buffer and where we didn't have a buffer. Here's the last lesson on titrations. In step 2 here, this is not a buffer because we essentially have weak acid, HF, and pretty much only the tiniest amount of F minus that came off of it. So it's not really a buffer. If you look at our concentrations, our HF is 0.1 and our F minus is 0.001. That's just two different. I know it says H plus right here, but that's also the F minus. If I go over here to step 5, this is also not a buffer. This is the opposite. We have essentially all F minus and hardly any HF, so that's not a buffer. But where we did have a buffer was in step 4. Here. Because we were partway through the titration, if I were to graph this, and I were to graph the entire titration, it might look something like this. In which point, which is step 5 of the lesson, and we are at 10 milliliters. The end point ended was something like 43, 0.1 milliliters. So this would be at 43.1 milliliters of base. Well, step 4 right here, we're only at 10 milliliters. So we are, if that's half, we're about right there when we're doing step 4. And this could be considered a buffer pretty much anywhere from here all the way through here. I think some might even argue it goes a little farther. So that's your buffered area, because in that purple area, you have both significant weak acid and weak base. Now, of course, the most obvious buffer is right smack in the middle of the titration. So right here, if you're ever asked to pick where a buffer is, that would be your best answer right there. But where we are right here is also a buffer, because if you look during the calculation, we had 0.0549 molarity HF and 0.0166 molarity F minus. Now the HF, there is more, but there's a significant amount of both, enough to say that this would be a buffer, and the buffer happens to have a pH of 4.48. And that should do it for this lesson.